Welcome to a lesson on vectors. In this video we'll be looking at the operation on vectors, and then we'll be looking at some applications. So specifically the operations that we want to talk about are addition and subtraction, so adding and subtracting two vectors or more than two vectors, and then scalar multiplication, which is taking a number that's not a vector, just a number, and multiplying it by a vector. And then we'll look at a couple applications using vectors, specifically applications that focus on direction or bearing or heading. All right, so how do we add two vectors? So let's say we have two vectors, u and v, and we want to add them together. So to add vectors, it's really easy. We just add the corresponding components. So remember, components, each vector has an x and a y component. So when we add two vectors, we're just going to add their x components and we're going to add their y components. And the result when we add two vectors is we get another vector. So we need an x and a y component. Visually, kind of what's happening, if we wanted to see what graphically how we add two vectors, let's just kind of look at a very generic example. Say we have two vectors u and v. And we'll just both draw them starting at the origin. U points into the first quadrant and V points into the second quadrant. And just again, this is a very intuitive kind of idea, but let's just to kind of illustrate the point here, let's imagine that vector U in the first quadrant represents sort of the flight path of an airplane, and let vector V, which points into the second quadrant, represent a gust of wind. Or wind that's blowing, so the wind is blowing kind of across the path of the airplane. So if we wanted to add the vectors, we're going to take vector v and we're going to move it. So instead of it being at the origin, we're going to move it so it's at the tip of the arrow for vector u. And then, so that's u plus v is that new vector that we kind of moved out there. Again, they're the same vector, they're same magnitude and same direction, so it's equal. And then we would draw the result vector. So from the origin to the end of the two vectors, that would be vector u plus v. And again, intuitively, that would just represent where the plane is actually going to fly, right? Because it's headed towards u along the u vector, and the v vector is pushing it sort of to the left, and so it will be a little bit off of its main path, a little bit to the left. So that's u plus v. And again, we're just putting one vector on the end of the next vector. And if you have multiple vectors that you're adding together, you can just kind of do the same thing. Just keep putting one vector at the end of the next vector. All right, so what about if we subtract two vectors? Same thing, we're just going to subtract their components. So subtract the x components, subtract the y components, and you get a new vector. Graphically, again, the same thing happens. You have vectors u and v. We could think of, just like we did before, we have u, and you can move the plus v vector to the end of u. And then, remember, we're doing subtraction, so instead of plus v, we want to look at minus v, and so the minus flips it in the opposite direction. So and then we draw our resulting vector. So from the origin to the end of v, we're going to get the new vector u minus v. So this time it pushes the original u vector kind of more to the right, or rotating it more, I guess rotating it clockwise. All right, so that's kind of what addition looks like. And then the third option, so that's addition and subtraction. The third option is multiplying a scalar. So let's just say c is some number. If we want to multiply c times vector u, we're just going to multiply each component of the vector. So you're going to take that number out front and multiply it by the x component, and then multiply it also by the y component. Which hopefully this idea again is fairly intuitive. If you take some vector u and you multiply it by a constant, it's going to make that vector either shorter or longer. Okay, it's just going to kind of scale it, which is kind of where we get that term scalar from. It's just scaling, and it's making it longer, it's making it shorter. When we saw with the subtraction, if that scalar was negative, it could flip it and point in the opposite direction. Okay, complete 180 degrees opposite direction. All right, so that's sort of the idea behind what we're doing. So let's actually look at some specific examples. So say we have vector u, which is negative 2, 2. And then we have vector v, which is 1, 3. And so first, let's just look at doing u plus v. So to do u plus v, let's first do it with algebra, and then maybe we'll look at just visually what's happening too. So with u plus v, we're going to have a negative 2, 2 plus 1, 3. And remember, when we add vectors, we just add their components. So I'm going to have the x components first. So negative 2 plus 1. And then the y components are going to be 2 plus 3. And so the result is a negative 1 and a 5. And again, if we wanted to sort of just visualize that, again, it's always kind of hard to sometimes draw these. But we have one vector that goes negative 2 and positive 2. So it's going to go 2 units to the left and 2 units up. So that's vector u. And then vector v is 1, 3. So it's from that endpoint, we're going to go to the right 1, and then we're going to go up 3 more. So 1, 2, 3. So from this point, we're going to go to the right 1 and up 3. So it's going to be something kind of like that. And then we want to draw what is the addition of that. So u plus v would start at the origin and go to where that arrow ended. And so that would be left 1 and up 5 from the origin. So from the origin, it goes left 1 and then up 5 units. So that is what our the sum of u plus v would look like graphically. All right, let's try a scalar multiple. We have a negative 3 times u. So if we actually write out our vector, that's a negative 3 times u, which is a negative 2, 2. And so when we multiply a scalar, we're just going to multiply the scalar times each of the components. And so we're going to end up with a positive 6 and a negative 6. And again, just we'll look at this one real quick visually as well. If we have, again, vector u is a negative 2, 2. So we go over 2, and we go up 2. So vector u goes this way. Okay? So negative 3 times u, that means it's going to be 3 times as long, but it's going to point in the opposite direction. So it's going to go in the opposite direction, and it's going to be about 3 times as long. And so this is going to go to 6 and negative 6. So that's our vector here. So this is negative 3 times u. All right, a couple more examples. We have 2u plus 5v. So that means we have 2 times the vector negative 2, comma 2 plus 5 times the vector 1, 3. So when we multiply scalars, remember we're going to first multiply the components, both components, and we're doing the multiplication just following normal rules of operation. Multiplication happens before addition. So our first vector is going to become a negative 4, comma positive 4 plus a 5, comma 15. And then now that we've done the multiplication, all that's left is to do our addition. And when we add, again, we're just going to multiply, or sorry, we're going to add the x components, and then we're going to add the y components. So 4, which that should be equals there. So we have the vector negative 4 plus 5, and then 4 plus 15, which turns out to be 1, comma 19. And then one more here, we have 3v minus 4u. Now be careful, this is a minus, and I flipped the vectors around, so it's not a uv order anymore. So you have to pay attention to get the right numbers and the right variables. So we have 3 times the vector v, which is 1, 3, minus 4 times negative 2, 2. So we need to go ahead and distribute the 3 into the 1, 3 vector. And then with the minus 4, you could just distribute the 4 and leave it as a subtraction of vectors, which we'll go ahead and we'll do it that way since we haven't done a subtraction yet. You could also distribute a negative 4 and then turn this into just a plus. So we're going to have the vector 3, 9 minus the vector negative 8, 8. And again, I could have also multiplied the negative in there, which would have changed all the signs here. So when we subtract, we're going to subtract components. So we're going to have 3 minus a negative 8, and then we're going to have 9 minus an 8. And so our result vector is going to be 11, comma 1. All right, so again, that's adding vectors, subtracting vectors, and doing scalar multiplication is super easy. It's just like distributing numbers into parentheses. You just add the components or you multiply through the components. All right, when we talked about vectors, again, we could also think of them in ij form. And again, you can write these interchangeably between ij form and the component form that we were just looking at. But let's just try a couple examples here using the ij format. So we have u is 3i minus j, and v would be 2i plus 3j. So remember, if you wrote this in component form, it would be 3, negative 1, and then this would just be 2, 3. So you could convert everything into component form. You could work it with it in ij form. It doesn't really matter. It's just pick one and whichever is more comfortable to you and work with. I usually particularly like the component form, just the visualization for the way I see things is helpful. But we'll go ahead and do it using ij. So we have u plus v, which will equal 3i, and sometimes if you can write the I as a vector with just an arrow. Since I and j are unit vectors, we can also write them with a little hat symbol. So 3i hat minus j hat plus 2i plus 3j. Now technically, I might want to put these in parentheses. It's not necessary here because it's an addition. If this was a subtraction, I would need parentheses around the second one, around vector v. But we are adding this vector plus that vector. And so remember, when you add vectors, we are going to add their components. So let's first do the I components. So for I, we have a 3 and we have a 2. So 3 plus 2i. Plus, and then we have our j components, and for j we have a minus 1 because it was minus j over here for vector u, and then we have a plus 3 for vector v. And so our end result is that we're going to have 5i plus 2j. Okay. Next one, this is, so we have the magnitude of u plus v. So again, magnitudes sort of look like absolute value, but we need to pay attention again to order of operation. U plus v is inside the magnitude, the absolute value symbols. So we need to do the magnitude of u plus v. So it's not the magnitude, and which is different than number 3. So in number 2, we're not taking the magnitude of u and adding it to the magnitude of v. We want to take the magnitude of 5i plus 2j. So if you remember magnitude, it's the square root of a squared plus b squared. So we're going to have the square root of 5 squared plus 2 squared, and that's going to be the square root of 25 plus 4, or the square root of 29. Okay, and that's as simplified as we can get it. So again, notice the difference between number 2 and number 3. In number 2, the addition of the vectors is inside the magnitude, so we had to do the addition first. Where number 3, the addition is outside the magnitude, so we want to do the magnitudes first. So what is the magnitude of u? So again, we're going to do a squared plus b squared and the square root of that. So we're going to have the square root of 3 squared plus a negative 1 squared. So that's the magnitude of u. And then we're going to add that to the magnitude of v, which would be 2 squared plus 3 squared. And so that's going to be the square root of 9 plus 1 plus the square root of 4 plus 9. And that turns out to be the square root of 10 plus the square root of 13. And that's as simplified as we can get it. We can't add these two square roots together, and there's nothing I can do to simplify them in any way, really. So notice that this order of operation is important. If you do the addition first and then find the magnitude, you get the square root of 29. But if you do the magnitudes first and then add, you get something completely different. All right, so let's kind of begin looking at some application. Again, then the applications we're going to look at are all the two that we're going to talk about deal with heading, or we want to think about direction, often like in navigation or applications like that. There's a lot of different ways to talk about heading depending on the context that you're in. For example, in the this little illustration image I have here of a compass. Again, we have north, south, east, and west as our normal cardinal directions, and for the most part, that's the way we're going to deal with things. And notice on this particular compass, it uses 0 degrees to represent due north, and then 90 degrees represents due east, and so it continues increasing in a clockwise direction until you get all the way back to basically 360 degrees would be the same thing as 0, so due north. Okay, so that's one way you can do it, but it's not the way we're going to do it in here for this class. But we do need to make sure we know the north, east, south, west cardinal directions. So the way we're going to kind of approach this is we're always going to, well, for the most part, we're always going to base our headings off of a north or a south direction, or north and south angle. So what I mean by that is we might talk about an angle being north 20 degrees west. So that means you're going to start north and you're going to turn 20 degrees west. Or maybe we have south 75 degrees east. So that means you start south and you turn 75 degrees towards the east. And then a third one, which you might see in WebAssign, would be 40 degrees north of east. So this is a little different because it's actually basing your direction off of the east. So it's saying if you're east, you want to go 40 degrees north of that. So let me just draw what those look like. So we have north 20 degrees west. And you could think of that as being west of the north direction. So we know north, again, is basically the y-axis. So if we're going to start north, we want to turn 20 degrees west. So that means we're going to be in the second quadrant, and we're rotating from the y-axis a distance of 20 degrees. So this is north 20 degrees west. For the second one, we have south 75 degrees east. And you could maybe think of that as east of south. So again, north is the positive y-axis, which means south is the negative y-axis. So starting from the south axis, from the south direction, we are going to rotate 75 degrees towards east. So this would be south 75 degrees east. Okay, and so again, you could see it as south 75 degrees east, or you could talk about it as being 75 degrees east of south. And for the last one, it's 40 degrees north of east. So again, pay attention to the wording there. It's 40 degrees north of east. So we're going to start from the east, which is the positive x-axis, and we're going to rotate 40 degrees towards the north. So that would be 40 degrees in a counterclockwise direction. So this, we could also write this vector as north. You know, how many degrees is that north and east? Well, if it's 40 degrees here and up to the north axis would be a total of 90 degrees, then we could also think of this as north 50 degrees east. Okay, so there's different ways you could phrase it. It's north 50 degrees east, or you could think of it as 40 degrees north of east. All right, so let's actually look at a couple applications. The first one we'll look at deals with just sort of a shark swimming around, and he has a really good sense of direction here. So he's going to leave his normal feeding grounds, and he's going to travel 5 miles due north, I mean to the mile in that exact direction, and then he's going to travel 8 miles due west. So again, he's got a really good nose for direction here. So we want to just first draw a diagram that illustrates sort of the journey that the shark makes, and then we want to determine the vector a second shark would make if he was starting at the feeding ground and trying to swim and meet up with the first shark. And we want to express our answers using our IJ form. So we want to first draw our vector diagram. So we'll just draw our y-axis, which is north-south. And then we'll draw our east-west x-axis. So again, north and east, south and west. So the shark first swims 5 miles due north. So that's along the positive y-axis. So he swims 5 miles. And then he swims 8 miles due west. So we could draw this vector here at the origin, starting in the origin and pointing 8 miles due west. Since we're thinking, we might be thinking in terms of addition here, because we're trying to find his total journey. We can just go ahead and write it. We can draw the vector sort of at the tip of the first vector. So from where he swam 5 miles north, and then he turns and heads 8 miles west. Now, again, just to, if you wanted to try and draw the best graph that you could get, I would encourage you to try and think about the scale. So this first distance is 5 miles. The second distance is 8, so it should be longer than the first. It should almost be about 1.5 times as long as the first one. You don't have to have it to perfect scale, but it can be helpful if you can sort of get appropriate angles, appropriate distances for your vectors. Okay, so that represents our diagram. That represents the direction that the first shark swam. And so we want to, if we wanted, we could express these as vectors too. So 5 miles due north, what would that look like as a vector? So a vector, again, has to have a horizontal and a vertical component. And I'm going to write these in component form. So to swim 5 miles north means there is no direction, there's no component in the horizontal direction. So the x is 0 and the y is a distance of 5. So this first vector is swimming 5 miles due north. We could think of as the vector 0, 5. The second vector is swimming due west. So now there are 8 miles in the horizontal direction, and since it's to the left, we want to think of that as a -8. And since it's completely horizontal, there's no vertical component, we're going to be having a 0 for the y component. So we're going to have the two vectors 0, 5, and then the vector negative 8, 0. So those represent the vectors for the path of the first shark. So the second part is that we want to determine the vector that a second shark would swim from the feeding ground to catch up to the first shark. So to do that, that means we're going to start here at the origin, and we want to swim. We want the second shark to swim. Oh gosh, that's horrible. So the second shark starts at the origin at the feeding grounds, and he's going to swim straight for where the second shark is located. He's not going to swim north and then west. He's going to go in a northwestern direction. So what we looked at a few minutes ago is if you take one vector and put it on, and then attach a second vector to it. If we add it on the tip of it, this is actually the sum of the vectors, so that's u plus v. So in order to find the vector for the second shark, we just want to add these two vectors together. So we're going to have, and I want to do this in ij format, so let me change these vectors. Negative 8, 0 would be a negative 8i, and then 0, 5 would be 5j. So if we add these two vectors together, we are going to get negative 8i plus 5j. Okay, so this is the vector in ij format that represents where that second shark needs to swim. So it's starting at the origin, and it's it's that straight distance to where the first shark was located. Okay, next for our shark, we want to figure out how far will the shark have to travel. Well, we already know, again, we know what our picture looks like. So we go north 5, we go west 8, and then we're going to go diagonally. So that's the vector we're looking at. That was negative 8i plus 5j. Okay, so to find out how far he would have to travel, the second shark, that means we want to find the magnitude of this. So what is the magnitude of negative 8i plus 5j? All right, so again, for magnitude, we need to take the square root of a, which is negative 8. So we're going to have a negative 8 squared plus a 5 squared. And so that's going to be the square root of 64 plus 25. And that's going to be the square root of 89, which, again, I don't think we can really simplify that. So we'll just leave it there. If you wanted, you could find that as a decimal. But this so square root of 89 miles is how far the second shark would have to swim. And then the third question is we want to know what heading will he have to take. So again, he's not going due north and then due west. We want to find the direction. So there's two angles that we want to find. There's the angle between our vector and the x-axis, or we could find the angle between our vector and the y-axis. And when we're talking about headings, again, we want to talk about them from the north or from the south. At least in this example. So we want to talk about this vector here. So between our vector and the y-axis. So there's several ways we could get to that. In this particular problem, we already have actually a right angle up here because he went north and then west. So this turns out to be a right triangle, and we want to know this angle here and we know the opposite side from this angle. We know the opposite and the adjacent. So if you know the opposite and adjacent and you're trying to find the angle, how do we do that? Well, we have a trig function, specifically tangent of theta, which we know tangent of theta is the opposite over the adjacent. So that means we know the tangent of theta is going to be 8 miles over 5 miles. And again, that's not one of our nice unit circle values. So in order to find theta, we're going to have to do an inverse tangent of 8/5. And if we use our calculator, we'll end up getting that turns out to be 57.99 degrees. All right, let's try one more example. It'll be sort of similar in nature, but maybe a little bit more complex in the information that we're given. So we are launching a rocket with a heading of north 65 degrees east with an airspeed of 120 miles per hour, and the wind is blowing due south at 20 miles per hour. So we want to again draw a vector diagram to illustrate the rocket's path, and then we want to express the velocity of the rocket's initial heading in component form. So a couple terminology things to point out here. We have velocity and we also have speed. So notice speed is just a number. It's 120 miles per hour. So speed is a scalar. Okay, velocity is going to include magnitude and direction. So velocity is going to be a vector. Okay, so whenever you see velocity, think vector. Whenever you think speed, think scalar, or more specifically, think magnitude. Okay, so there is a vector that represents the heading of the rocket, and we just know its airspeed is 120 miles per hour. So let's draw our vector diagram here. Again, this one's going to be a little harder to figure out, but it's not too bad. All right, so there's north. So we're told it's launched in a heading of north 65 degrees east. So it's going to go from the north axis 65 degrees rotating in the east direction. So that means it's going to rotate from north 65 degrees. Okay, and so this is our vector. So this is north 65 degrees east. Okay, and we know that its airspeed is 120 miles per hour. Okay. At the same time, we have a wind that is blowing due south at 20 miles per hour. So it's going to go due south. Again, I'm probably not drawing this to scale very well, but this is 20 miles per hour. So notice in this case too, I could have drawn the 20 miles per hour off of the tip of the first vector. So it would have been over here. I just chose to draw it here at the origin. It doesn't really matter. So that's what our graph would look like, our illustration. We then need to figure out the velocity of the rocket's initial heading. So what I mean by this, by the initial heading, when we're talking about this, I want to deal with the heading without the wind. So let's just ignore the wind for the moment. So we know it's heading at north 65 degrees east. So we need to figure out what is the x component, and we need to figure out the y component. So we need to figure out the x and the y component, and that's based off of the 65 degree angle. But the 65 degree angle, notice it is outside. So we have this right triangle here, if we thought of that as being a right triangle. So if this is 65 degrees outside, what is the angle inside? Well, 90 degrees minus 65 is going to be 25 degrees. So I know that this angle in here is 25 degrees. And so if we wanted to find our components, we have an angle, we have an opposite side, we have an adjacent side, and we know the hypotenuse. So I could express the x and the y components using a right triangle trig. So I know that the sine of 25 degrees has to equal y over 120. And similarly, we know that the cosine of 25 degrees is going to equal x over 120. So if we solve each of those for x and y, we will get x will equal 120 times the cosine of 25 degrees, and we have y is equal to 120 times the sine of 25 degrees. So what does that vector look like? Let's call this vector v. V for velocity. It has a horizontal component, which in this case that's our x value. So we're going to have 120 times the cosine of 25 degrees, and then its y component is going to be 120 times the sine of 25 degrees. Now again, the key to this, usually cosine is going to be x, sine is going to be y. Where did the 120 come from? Remember, the 120 is the magnitude, it's the speed of the rocket. Where did the 25 degrees come from? Well, that's the angle inside our triangle, okay? It's not the 65 that we deal with, because the 65 would actually represent sort of a triangle up on the top, and that's not what we're trying to find. We want the bottom. We want the horizontal and vertical components. So we now have the velocity of the rocket's initial heading. So next we want to find the velocity of the wind. So again, we know the rocket was heading northeast at some velocity, which we just found. We know the rocket, and the wind is pointing due south at 20 miles per hour. Okay, so this one's pretty easy. Let's call this, so we have a variable name, let's call this W. Okay, so the W for the wind. And we know the velocity for the wind. Again, since it's due south, we don't have anything fancy we need to do. There's no horizontal component, so it's just 0 for x. And it's 20 miles per hour due south, which means it would be negative 20 for the y component. All right, so we now have our velocity for the wind. If you remember, we already knew the velocity of the jet. It was 120 times the cosine of 25 degrees, and then 120 times the sine of 25 degrees. So we now know both vectors. We know the velocity for the jet, or for the rocket, and we know the velocity for the wind. So the next question is, we want to determine the true velocity. Okay, so what we mean by true velocity is we want to find the velocity of the rocket, this time with the wind. Okay, so where is the rocket actually going to travel with the wind pushing it south? Okay, so again, if you remember, to figure this out, we're combining the two vectors together. So we want to add them. So we have our velocity vector, and if we move our wind vector over here, so here's our wind vector. So then we have a resulting vector. That resulting vector comes from the origin, and it goes to where the wind vector will end, and that is the velocity vector of the rocket plus the wind vector. Okay, so we have to do the velocity of the rocket plus the velocity of the wind, which is going to be 120 times the cosine of 25 degrees, and 120 times the sine of 25 degrees plus 0, negative 20. So we add components, we add the corresponding components, so we're going to have 120 cosine of 25 degrees plus 0, which we don't need to write, and then we have 120 times the sine of 25 degrees plus that negative 20, so minus 20 there. And we can go ahead and compute this all with our calculator just to get something maybe that makes a little more sense here. And so we get 108.76 for the horizontal component, and then we get 30.71 for the horizontal component. And those are that is the velocity of where the rocket's actually going to travel, and those units would be in miles per hour, because we're still talking about speed basically. It's just now it has magnitude and direction, not just magnitude. All right, so next we want to figure out what is the true speed. So remember, true means when we say the word of true in there, we're talking about how fast is the rocket actually going to travel. So we know it's launched, its initial launch was 120 miles per hour, but the wind is coming into play. So we want to figure out how fast is it actually traveling. And again, we're talking about speed, so we want to find its magnitude. So what is the magnitude that the rocket will actually travel? And we just found its vector. So we knew v plus w was equal to 108.76 comma 30.71. So we know what the velocity is, so to find the true speed, we just need to do the magnitude of v plus w. So we're going to have the square root of this 108.76 squared plus 30.71 squared, which if we use a calculator, that comes out to be 113.01 miles per hour. Now, just to check the whether that's a reasonable answer or not, let's look back at the original speeds we had. We had 120 miles per hour for the original rocket, and we have a wind speed of 20 miles per hour. So if the velocities of the rocket and the wind were pointing in the same direction, at most we could have 120 plus 20. So the highest speed this rocket would reach would be 140 miles per hour. If they were pointing in exact opposite directions of each other, then again, the highest we could possibly have, or in this case, the lowest speed that we could possibly have, would only be 100 miles per hour. Okay, so if they're going in the same direction, if the wind is blowing from behind the rocket, pushing it forward, and they're parallel to each other, then we can add the two vectors together and find the maximum. So just by the original speed of the rocket, with including the wind, the fastest it would fly is 140 miles per hour. If the wind was pointing completely against the rocket, then they're sort of going to negate each other a little bit. So we have 120 miles per hour minus the 20, and that gives us 100. So looking at the answer we found, it turns out to be somewhere in between. So again, that's not a perfect proof that we have the right answer, but had we come up with a number that was outside of, so it was not between 100 and 140, then we know for sure that we made a mistake somewhere. So that answer does seem reasonable. All right, the last thing that we want to look at is how do we find the true direction of the rocket, and we want to express it as a heading. So again, when we think of heading, we want to talk about an angle from the north or from the south. Okay, we want to find out what is the heading from the north or from the south. And so that can really just boil down to where is the vector actually heading? So we know it's 108.76 by 30.71. So we know that's the actual velocity of the jet. And so if we wanted to draw that velocity, okay, it's a positive x coordinate and a positive y coordinate. So it is still flying over here in the first quadrant. Okay, and we could even think of there being a right triangle. So we know the x component is 108.76. We know the y coordinate is 30.71. And we are trying to find the angle. So how do we find the angle? Well, in this little right triangle we have, we could think of there as being an angle here, all right? That angle is, from that angle, we have an opposite side of 30.71 and we have an adjacent side of 108.76. So we know that, again, the tangent of theta is going to be 30.71 over 108.76. But we want to find theta, so we're going to have to do our inverse tangent. So theta will equal the inverse tangent of 30.71 over 108.76. And that comes out to be an angle of about 15.77 degrees. Okay. However, that's not our answer. This is 15.77 degrees north of east. So depending on what your angle, which heading you're trying to find, that could be an acceptable answer. But you would have to say it is north of east. If you don't include this statement, that 15.77 degrees is meaningless. Okay. The other option, which again, if we wanted to express this as a heading, I like to express them as angles from north or south. So to do that, we need to figure out what is the angle from the north axis. So remember, north is the y-axis. So I really want to express it as this angle here, which is easy to find because we already know theta, so we can find this angle. We can just take 90 degrees minus that 15.77 degrees, and that's going to give us 74.23 degrees. So I could express this same angle as north 74.23 degrees east, or you could even express this as 74.23 degrees east of north. Now again, usually we like to express it in this format. Okay. As you're doing your homework, you may need to enter it in one of these other two options as well. You just have to pay attention to how your answers are formatted. Okay.